Chapter 7.6 is about the pressure or total force on a plate in a fluid. Usually water we'll be dealing with. Let's talk a little bit about some pressure physics. What are the units of pressure in US units? It's usually pounds per square inch. Which is abbreviated PSI. Is 1 PSI a lot? Well, I have something that weighs a pound here, full bottle of water about half a liter, and I have something with an area of about 1 square inch. So if I put that there to concentrate the force on 1 square inch, then my hand is feeling 1 PSI of pressure right there. So it's not negligible, but it's not a lot of pressure. 1 atmosphere of pressure, let me try that again. Which is abbreviated 1 ATM, is 14.7 psi at sea level. So imagine 15 of these basically stacked up on 1 square inch. That's the amount of pressure each of us is feeling from every direction on every part of our body if we're at sea level or reasonably close to sea level like we are in Michigan here. So that's the US units. Metric units, force, instead of pounds for force, we're going to use newtons. Newtons. And instead of square inches, we're going to use square meters. So 1 Newton per square meter has a definition of 1 Pascal. Is that a lot of pressure? Well, remember, 1 small apple weighs about a Newton. So if I mash this up and spread it out over 1 square meter, that's basically the size of a card table, right? That's 1 Pascal, so that's not very much at all. So 1 atmosphere ends up being 101.3 kilopascals, and it's so common to use kilopascals that we even have a new measurement called 1 bar. Bar is a Greek word for pressure or weight, ancient Greek at least, and 1 bar is 100 kilopascals. So 1 bar is just about the same as 1 atmosphere. So let's talk about what kind of pressures things experience when they're immersed in water and gravity is pulling on the water and causing pressure. So the pressure at depth D I'm using capital D here so I don't get it confused with a lowercase d like dx or dy, is this formula rho times g times d. Rho is the density in kilograms per cubic meter. Do you remember the density of water in kilograms per cubic meter? I had it in a previous video. It is 1,000 kilograms per cubic meter, at least at a reasonable temperature and pressure. G is the acceleration of gravity. Which is, we're going to use 9.8 meters per second squared. When I was in high school, people said it was 9.81. Maybe I was just in a location that was closer to the center of the Earth or something. But we don't really need high precision here anyway. And D is the depth in meters. So the idea here, we've got the surface of the water here and some item down here, and its depth is D. The lower it goes below the water, the more water above there is pressing down, and pressure is an omnidirectional thing. So even though the water is pressing down, that presses on the water here that then presses sideways. So it doesn't really matter which direction we're talking about the pressure. So the farther down you go, the more pressure there is. If you've gone in a swimming pool and tried to dive down to the bottom, you might have felt the more and more pressure, especially on your ears. What is the pressure at 1 meter underwater? Well, that would be rho times g times d, like we just said. Rho is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. D is 1 meter. Multiply that all out, you get 9.8 kilopascals. Is 9.8 kilopascals a lot? Well, just ordinary atmospheric pressure is 100 kilopascals. This is about 10. So this is about 1/10 of an atmosphere. How much farther below water do you have to go to get a pressure of 1 atmosphere of water in addition to the 1 atmosphere already pressing on us? Well, does it look like it's a linear or even directly proportional relationship between depth and total pressure? And so if going 1 meter underwater gives you 1/10 of an atmosphere, it would be 10 meters underwater. Pressure is directly proportional to depth. So 10 meters of water gives you about 1 atmosphere. So here's a question I often had growing up, maybe you did too. Why don't we, like if you wanted to walk across to an island in a river or something, and your head would go underwater, why not just have like a tube or a hose up to the surface? It seems like the pressures involved aren't all that great, so why not just do that? I mean, we do that with snorkels, but why don't we have really long snorkels? Well, let's talk about the force on an area. It's the pressure times the area. The pressure is newtons per meter squared. The area is meters squared. So altogether we get newtons. It kind of makes sense. It's pretty much the opposite of what we were saying up there, right? So if you had a really long snorkel to the surface, how much force would there be on your rib cage? Let's say you were 5 meters deep. Well, the force would be the pressure times the area. The pressure, if you're 5 meters deep, how much pressure is that? You could use rho times g times d. It's not a bad exercise. But we already saw that at 10 meters you had 1 atmosphere or 100 kilopascals. So this would be, the pressure would be basically 1/2 atmosphere or 50 kilopascals. The area, what's the area applicable to your rib cage or something? I don't know, I'm not a biologist. I'm going to guess that it's like 30 centimeters by 30 centimeters, which would be about 1,000 square centimeters, which is about 1/10 of a square meter. So this is the approximate rib cage area. Because your lungs are trying to expand and contract, right? Mostly if they're getting pressed on by all the water and the rib cage, they're trying to expand against that water. So if you multiply this out, you get about 5,000 newtons, which turns out to be about, in Earth gravity, equivalent to 500 kilograms, since g is approximately 10. So that's 500 kilograms. Let's call that somewhere between 5 and 10 people standing on your lungs. That's going to make it a little hard to breathe. And here you might be saying, well, the orientation of pressure, I mean, it's not pushing you down really. Well, some of it's pushing in from the front, some is pushing in the back, some is pushing in from the sides. So it turns out to not matter. You just could not draw in a breath with a snorkel that long.